So let's move on to logistic growth models. So as we talked about with the exponential growth model, B and D were constant regardless of the population size. Now we'll indicate B prime and D prime representing the birth and death rates of the population. And we're going to set a condition here. So the growth rate at any particular time is a function of the birth rate. And that birth rate is the maximum birth rate that a species can achieve in a particular environment minus A times N. And so what this is basically as N increases, you're going to have a proportional decrease in the birth rate of the population. And the rate of that decline is going to be determined by this parameter A. And similarly, for the death rate, you have some minimum death rate when the population size is low. But then as the population size increases, the death rate also increases as dictated by this parameter C. C times NT indicates that as N increases, the rate of death increases. Both A and C are going to be very small numbers in most populations. So substituting B prime and D prime into our standard exponential growth equation gives us the logistic growth equation. So now notice that the change in population size is a function of the maximum growth rate or birth rate of that population minus some factor that indicates the effect of population size on birth rates, and the death rate plus some factor which indicates the effect of population size on the death rates. And if we go through some algebra and we define a quantity K, as we see in the logistic growth equation, we can jump from here to here fairly simply, and I'll show you that on the next slide. Just quickly here, so we started with the equation that we had previously. We just rearranged the terms, and now notice you have this term B max minus B min. Well, that's just R max because you have your maximum birth, minimum death rate, and now you have this term A times N sub T plus C times N sub T. Pull out the N sub T, and in the next step you are pulling R max out of this part of the equation, and that results in now 1, and you have N sub T times A sub T over R max. And we define K as R max divided by A plus C. So if you look at that, you see that that's just the inverse of what we have here, and so that leads to the K in the denominator in the classic logistic growth equation. So to get a sense of what we're talking about here, if you look at a graph of per capita growth rate, or little r, along the y-axis, okay, population size on the x-axis, basically what we're saying with the birth rate is that we start at some maximum birth rate at the small population size, and that as population size increases, that birth rate declines. The slope of that relationship is equal to A, okay? So A tells us how rapidly does birth rate decline as population size increases, okay? Similarly, for death rate, you might have some very low death rate at low population size, and as population size increases, death rate also increases, and the slope of that relationship is indicated by C. Okay, so basically, as C and A get larger, that means that the decline in growth rate is more rapid as population size increases. And the other thing that's interesting is it also decomposes the effects of population size on either birth rate or death rate. So if we think about birth rate first, what things might lead to a decline in birth rate with population size? Well, can't ask you, but what you might say is, food availability. As you get more individuals, you have less food per individual, so maybe the number of young they kick out drops. Territory availability, if you're talking about a territorial species, once it gets filled up, you can't find a territory, so you're not going to be able to reproduce. Stress, maybe as population size increases, there's more aggressive interactions leading to higher stress among females and a lower birth rate. So lots of things. Similarly, for an increase in death rate with population size, again, food decreasing could lead to higher mortality, lower survival. Predation, as animals become in poorer condition, they may be more vulnerable to predation and disease. Again, if you're lots of individuals in poor condition, that could lead to higher rate of mortality from disease. And you put this all together and you get the classic logistic growth curve, where the population initially increases rapidly, but as population size increases, that starts to put a downward pressure on the rate of growth population until it finally reaches an equilibrium where the birth rate is equal to the death rate and the population size no longer changes, and that, of course, is K. Well, in addition to the classic logistic growth curve that you're seeing, another way of portraying this is as the growth rate of the population, delta N, so the number of individuals that are being added to the population in each time step. And notice what you get here. You get a maximum at about half of K. So K in this case is 100. That's our carrying capacity. That's where we level off and stop here. But notice initially you don't have much increase because you don't have very many individuals in the population. Even though they're per individual reproducing rapidly, there's just not many of them. As the numbers increase, then you start getting more and more added to the population. But now you start getting a brake put on growth rate because there's more individuals, lower birth rate, higher death rate, and it comes down. And what you'll find is that that is maximized at 1/2 of K, or half of the carrying capacity. So what we've got on the left here is this equation that predicts numbers over time. On the right, you have change in numbers over time. And finally, a third way that we can look at this is with the per capita growth rate, which of course is just little r. We divide both sides of the equation by n sub t, so now we have the change in the size of the population per individual in the population, and that's going to be equal to r times 1 minus n sub t over k. And so as n sub t increases, this quantity gets larger and larger and closer to 1, at which point it hits the maximum population size. And from that point on, there's no growth in the population under ideal conditions. So let's look at the biological interpretation of this term, 1 minus n sub t over k. Notice that if we take that term out, we're just right back to the exponential growth equation. So it's really this that transforms exponential growth to logistic growth. And the way you can think about this is that term 1 minus n sub t over k is an adjustment to R that represents the unused portion of the carrying capacity. So what happens when the growth rate to the growth rate of the population of n is much smaller than k? So this numerator is very small. This whole term then will be very small. This then will be very close to 1. And as you might expect, that's going to give you exponential growth. So initially, in a population even growing by the logistic growth equation, it's going to grow at a rate very close to the exponential growth prediction for that population. But if as n gets close to k, so now this term is close to the term in the denominator, this whole thing then becomes close to 0 because we have 1 minus something close to 1. And that's the point at which you have no further growth in the population. The the logistic growth model is derived from the exponential growth model. So they share many of the same assumptions. For one, geographic closure, no immigration or emigration. We're just talking about birth and deaths of individuals in the population. We also assume no individual variability. In other words, no variation among individuals of different age, sex, genetic structure, and so on. Everybody in the population is exactly the same. And though we start out with maximum birth rate, minimum death rate when the population is very small, we are assuming this very simple linear density dependence. So as the population size increases, for every individual added to that population, there's an incremental decrease in the birth rates. And for every individual added to the population, there's an incremental increase in the death rates. And that all the way along, that's just a nice linear relationship.